All right, so now for the last video from chapter 12, well, let's see. First, we're going to talk about 12.5, which is about turbulent flow and how you can sometimes predict whether that's going to happen. And we're also going to get to 12.6 in a minute. Okay, so basically what we've talked about, right, we spent a lot of time, right, volume flow rates and Bernoulli's equation. And remember, Bernoulli's equation only applied if we had laminar or streamline flow. But sometimes flow is turbulent, and it turns out there's a way to predict whether your fluid flow is going to be this nice laminar flow or turbulent flow. So if we're in a tube, we calculate something called the Reynolds number. So this capital N with the subscript R is known as the Reynolds number. And you calculate it, it's 2 times the density of the fluid times the speed of the fluid V times the radius of the tube divided by this quantity eta, where eta is the viscosity. So it's how resistant is the fluid to the flow. And the rule of thumb is if the Reynolds number is less than around 2000, it'll be laminar flow. So between about 2,000 and 3,000, you expect it to be kind of unstable, so it might flip back and forth between laminar and turbulent flow. But if Reynolds number is above 3,000, you would expect it to be turbulent flow. Okay, so let's do a quick example. So we've got an IV system supplying a saline solution at some rate, so 0.12 cubic centimeters per second. And through a needle with some radius and some length. So do you expect this flow to be laminar or turbulent? So first off, so we've got 0.12 cubic centimeters per second. So that is a volume flow rate. And of course it's cubic centimeters per second, but we need cubic meters per second. So I went ahead and did the conversion. 1 meter is 100 centimeters, but I need to cube it since it's cubic centimeters. So my volume flow rate is 1.2 times 10 to the minus 7 cubic meters per second. Okay, so now what we need to do, we need to calculate our Reynolds number, see how big it is. So we need a density, and so density, well, this is a saline solution, which is essentially salt water. So for our density, let's use 1,025 cubic meters. Or sorry, kilograms per cubic meter. And R, so we've got a radius, 0.15 millimeters or 0.15 times 10 to the minus 3 meters. And eta, well, you can look up values for the viscosity. So in fact, in your textbook, there is a table. So table 12.1 has these coefficients of viscosity. You look up water at 20 Celsius, then it's about 1. And again, just be careful. Notice the units here. It's millipascals times seconds. So I'm going to use 1 times 10 to the minus 3 Pascal seconds. Okay, so the only other thing we need is the speed V. But I've got a volume flow rate. So if you remember, volume flow rate is A times V, which means if I need my speed, I can take my volume flow rate, divide by the area. So my volume flow rate, which was 1.2 10 to the minus 7 cubic meters per second. Divide that by the area. Again, if it's a circular tube, pi r squared. Radius is 0.15 millimeters, or 0.15 10 to the minus 3 meters squared. So V is going to be 1.2 10 to the negative 7. Divide by pi. Divide by 0.15 10 to the negative 3 squared. So 1.698 meters per second. Okay, so now I've got everything I need. I can calculate my Reynolds number. So from the equation over here, Reynolds number is going to be 2 times the density 1,025 kilograms per cubic meter times the velocity, 1.698 meters per second, times the radius, 0.15, 10 to the minus 3 meters, divide by the coefficient of viscosity, 1 times 10 to the minus 3 Pascal seconds. So I plug all that in, 2 times 1,025 times 1.698 times 0.15, 10 to the negative 3, divided by 1, 10 to the minus 3, 522. And the Reynolds number really is just a number, so if you look at the units, all the units cancel out. 522, and if you remember, if the Reynolds number is less than about 2,000, you expect laminar flow. So since our Reynolds number is less than 2,000, we would predict that the flow through this IV tube is going to be laminar. All right, so now another thing we can look at is motion in a viscous fluid. So if we have an object moving through a viscous fluid, we can also define a Reynolds number for these objects. So here, this Reynolds number, there's a little prime because now this is the Reynolds number for the object and not the Reynolds number for the fluid itself. The density of the fluid times the speed of the object times the size of the object, L, times this coefficient of viscosity. And again, this will actually predict how the fluid is going to flow around the object. And if it's less than about 1, you expect laminar flow around your object. So it's going to be something like point A here, so where the fluid keeps these kind of streamlines around the object. If it's from 1 to 10 or so, you expect turbulent flow, and from 10 to, larger than 10, it's going to be unstable. So again, this is so turbulent. So this is the middle picture here, where you've got, it's partially turbulent and partially streamlined, and then unstable flow is when you have very large Reynolds numbers. Okay, now, so finally, real quick, so chapter 12.6, again, motion of an object in a viscous fluid. So we can actually do something, we can calculate a viscous drag. So if you think all the way back, what was this, like chapter 4 or 5, somewhere in there? So we were looking at drag forces, and we had some equations for drag forces. But now that we know something about fluids and viscous fluids, we can actually do something to calculate some of these drag forces. So if we have laminar flow, the drag force is going to be proportional to the speed of the object. Now, or if our Reynolds number for the object flowing through the viscous fluid, this n prime, is from about 10 to about 1,000,000, then it's going to be proportional to the speed squared. So if you remember all the way back to when we talked about drag forces, we said, well, sometimes it's proportional to the speed, sometimes it's proportional to the speed squared, and it's actually this Reynolds number can help us predict and decide which one to use. And again, if the Reynolds number is really, really big, like bigger than around 1,000,000, then things get more complicated. So if we have a small sphere, so if we have a sphere moving through a viscous fluid and it's moving slowly, so our Reynolds number is going to be relatively small. So the drag force is going to be 6 pi times the Reynolds number times the coefficient of viscosity times the speed of the object.